solve the equation log x minus 1 minus log x plus 2 is equal to negative 1. So this is a reminder that if you don't see a base, then the base of that certain log expression is just 10. So this gives me then, if I may, okay, we're just going to make the 10 visible in here. So log 10x minus 1 minus log of 10x plus 2, and that's equal to negative 1. And you could see the expression or the operation that separates the log functions or the log expressions. So we would have log to the base 10 of gives us just quotient, right? So if you see a minus sign separating the two log expressions, it's a property of the quotient of the logarithms, and the quotient, the property of logarithms stating the quotient of the two expressions expands it into the difference of the two logarithms. So this will give me x minus 1 over x plus 2, which is equal to negative 1. Okay. Let us now go to the interchanging of the logarithm to the exponential form. So my base is 10, so I would raise it to negative 1. This is my exponent. And that's equal to x minus 1 all over x plus 2. And 10 raised to negative 1 is just 1 over 10. That's equal to x minus 1 over x plus 2. So using the property of crisscrossing, okay, I would get x plus 2 here on the left side, and on the right side I will have x minus 1 times 10. And so x plus 2 is equal to 10x minus 10. And so I would have to arrange the expressions such that I would only have x expressions on the left and the numerical values on the right. So x, and then I get transform 10x to the left. This will give me negative 10 minus 2. So negative 9x is equal to negative 12. And my x here is equal to, it's not clear, okay. So my x here would be, we divide both by negative 9. Okay, now let us use this space. So we have x is equal to negative 12 over negative 9. This will give me, I have to divide both by, just simplifying, okay, divide both by 3. So I will have 4 over 3. So my x is actually 1.333333, okay. But you could get the decimal places or round it off to the nearest 10 thousandths, okay. So this is the answer for x. Okay, x is equal to 1.3333. Okay. Now, if you have doubt whether this x value here is actually the which is suitable, is it suitable for the value of x? You could see that when you substitute your x is equal to 1.33 here on this portion here, it yields to a positive value. So that would be like 0.3333, and on the other hand, it would be 3.3333. So therefore, this is a valid argument for the log expression or the log equation here, given here. Okay? But if you are in doubt, you can still do the manual checking. So just check whether the x fits into the logarithmic equation. So now we're going to review the logarithms with any base, okay, and the change of base property. So I'm presenting you two examples here, taken from your book. Okay, now our log 5 is also written as log base 10 of the argument 5. And if you check it in your calculator, this is equal to 0.6989, meaning that 10, okay, this is the interesting part, 10 to the 0.6989 is equal to 5, right? So that confirms our explanation in the beginning of the lecture, using the base of 10 to get the exponents, which are the logarithms of the bases. Okay, now in the second example, we have ln of 5. And ln of 5 could be written as log to the base e. As I've told you, this is a natural logarithm and its base is e. While on the other hand, the common logarithm is with a base 10. So we will have log to the base e of 5, and this is just equal to 1.6094 as stated. Okay? Meaning that e, because our base is a, raised to 1.6094 as the argument, or the exponent, indeed, will be 5. So this is what you call the change of base property. Now in calculus, you will learn why the e is important. Yes, it's very important actually in calculus and higher and advanced calculus computations, defining the integrals and derivatives and so on and so forth. Okay. So we now reach the definition of the common logarithms and natural logarithms. So as I am just reminding you that common logarithms have base of 10 and natural logarithms have a base of e. So log x means log 10 of x, really, right? And ln of x means log of base e to the argument x, where e is a constant, which is equal to 2.71828182846 infinity. Okay? So actually in your calculator, you have this base, or you have this expression e, as I've mentioned earlier, and you could reach that by pressing shift and ln. So shift ln gives you e raised to a certain box, and write 1 or press 1 into that box there, giving you e raised to 1. And e raised to 1 will give you a value of this. Okay? So it's a constant. So now, why is the base e and the common logarithm important? So let us have an example. X is equal to log to the base 5, 17. Okay. And essentially, this would give me an equally important exponential expression or form, which is 5 raised to x is equal to 17. And this gives me, because this one could be translated as log 10 5x, and the other one is translated as log 10 of 17. So if we are going to express the numbers or the expressions into a base 10 logarithms, this is what it is going to be. And this will give me, again, this is a power. Okay, this one denotes the property which is a logarithm raised to a certain power. Okay, And this one will give me a corresponding expression, which is x log 10 5. Okay, placing the x here behind your log of your logarithm expression. And on the other hand, we will have log 10 17, right? Okay. Now, if I have to solve for my x, then I would need to divide both sides by log 10 5, right? So log 10 5, and this will give me x is equal to, so I would just easily cancel that one, and this will give me log 10 of 17 over log 10 of 5, which is also equal to this will be equal to 1 over log 10 5 times log 10 17, right? And this will give me 1.4306 times log of 10 of the argument 17. So you could see that the base 5 logarithm of a number has its corresponding base 10 logarithm on your calculator and divided by the base 10 logarithm of 5. Okay, so why am I showing this to you? Because this will give us to another property of logarithm, which is the change of base. So the change of base property for logarithm, it states that log of a certain base a of the argument x is equal to log bx over log ba, or equivalently, log ax is equal to 1 over log ba times log bx. So notice that in this example, we expressed our logarithm expression into another base, 10. Look that our logarithm, our standard logarithm, or our given logarithm is expressed with the base 5, log 517. And we change it to a certain form wherein its base changed. So indeed, if we have a certain logarithm expression, we could also express this expression into another expression of different base. So therefore, in this case, this one became log of 10 17 over log of 10 5. Notice that your 5 came here and your 17 was there, and they have another base, which is 10, which is a common logarithm, 10. Okay? So this generalizes this property, or this, what do you call this? This expression for logarithms, indicating that if you have a certain base a, as in this case, you could change this base a into another base b, such that you have now another logarithm expression with an argument of x and a. Or similarly, it could also be written as like this. So you can separate your other logarithm expression, but with the same base also. So let us have an example. Find your natural logarithm of 29 using the change of base property with base 10 logarithm. Check your answer directly by pressing ln of 29. So our given expression here is ln, or natural logarithm of 29. And we are asked to have it with base 10 logarithm. So how do we do this? Remember that our natural logarithm could be expressed with the base e, right? So therefore, our ln of 29 will be having the common logarithm expression log of 29 over log of e. Okay? In other words, our natural logarithm of 29, when expressed into base e, will have this expression log to the base e of 29. And when we change it to the common logarithm with base 10, this will give us log of 10, 29 over log of 10e. Right? And in this case, we don't need to show the 10 because it's a common logarithm. So our answer is then taken as log 29 over log e. And if we are going to directly get the value of our ln of 29, in calculator, this will give you the value of, if you have your calculator, you can check it. Just press your ln. It's beside the log. Okay, so natural logarithm of 29 is directly equal to 3.3672, and still with an infinite series of numbers. Okay, now how about this portion here? So this portion will give me, what is my log of 29? I have my calculator here, and log of 29 gives me 1.4623 with infinite numbers after it, and log e is 0.4342. Okay, and this is exactly similar to the ln of 29 taken directly from a calculator. So this is also equal to 3.3672. So notice that they are similar. Okay, which agrees to the previous value you got using the change of base property.